Hello, I'm Jason Palmer, co-editor of The Economist's Espresso daily news app, and this is Babbage, a weekly conversation on science and technology. This week, we'll be checking in on Juno, the pioneering space exploration project on the verge of arriving at Jupiter.
It's one of the fastest things anyone's ever built, and it's got a rather difficult and technical maneuver to pull off to get into orbit at all.
And there's good news for card sharps, as new research suggests that the mind of a gambler can be read through tracking eye movement.
We were interested in whether this left-to-right oriented number line would manifest in an everyday game like Blackjack.
Got this boundary between game and science, which ends up just being an awful lot of fun to explore.
First, though, we're heading to Jupiter.
Ignition and liftoff of the Atlas V with Juno on a trek to Jupiter, a planetary piece of the puzzle on the beginning of our solar system.
Progress. Vehicle pod rates look good.
In 2011, the NASA spacecraft Juno launched, and it's been working its way across the solar system ever since. In just a few days, Juno will reach its destination, Jupiter, and begin the scientific part of its mission, a part with lofty goals, as NASA's principal investigator Scott Bolton explained on launch day.
So I've already had a good day because we launched successfully. When we arrive there and get into orbit, that's another good day. And then each orbit that we make successfully is another great day, because even if we just get a couple of orbits, we will have learned so much that we don't know now. The major science objectives of Juno are, one, to understand how Jupiter formed and what is it made out of. We want the recipe of solar systems, and we're at the ingredient list level. So we're gathering the ingredient list and understanding how Jupiter's structured.
Well, that first good day was 5 years ago, and the second one is coming up on July 4th. Here with me to talk through the Juno mission is science correspondent Tim Cross, who's had his keen eye on the progress of the spacecraft. Tim, first up, we heard Scott Bolton there say it would be exciting for Juno to complete multiple orbits. Why wouldn't we expect it to do so as so many space probes do?
Well, there's a couple of reasons. I mean, one, may not necessarily even complete one. This thing is going very, very quickly. It's going about 250,000 kilometers an hour. It's one of the fastest things anyone's ever built. And it's got a rather difficult and technical maneuver to pull off to get into orbit at all. It's got to decelerate, and it's got to get into a very specific kind of orbit that's going to take it right down close to Jupiter's cloud tops and then zoom way out back into space again. And if it doesn't hit that exact orbit accurately, we've got serious problems. And it's far enough from Earth that it's going to have to do all this itself. So if anything goes wrong during the middle of its deceleration, the probe has to be able to fix that itself, because at these distances it takes an hour or so for signals, even traveling at the speed of light, to get to and from the probe and Earth. So if anything happens, it's got to be able to fix itself, and we won't know whether it's worked until it has or it hasn't.
More nail-biting to come. And it's not the most friendly environment for a spaceship anyway.
No, it's not. This is the second problem. The whole area, all the space around Jupiter is full of really intense radiation because of the planets. It's got a really big magnetic field. So the only previous probe that we've sent to Jupiter, or sent solely to Jupiter, which was Galileo back in 1995, during its mission, it had all kinds of problems caused by the radiation. It had its cameras would white out, its main computer kept resetting. It plays havoc with the electronics. So Juno has this big armoured box in the middle, this sort of 200-kilogram titanium box that protects all its electronics and the computer and so on. That helps, but it isn't going to solve the problem. And NASA fully expects that over 2 or 3 years, the radiation is going to slowly fry the thing. And one of the questions is just how many orbits and how much useful time it'll actually be able to spend there before it just gets cooked.
So we've sent this hardened commando of a probe there. What kind of things are we hoping it can find out that we can't see from here?
Well, so you can learn quite a lot about Jupiter just by looking at it through telescopes, especially big ones like the Hubble, but there are some things you can't. So one of the big questions is, Jupiter's a gas giant. Its atmosphere is hydrogen, helium, and a scattering of other stuff. But one of the questions is what lies beneath the clouds. Does this planet have a core like Earth does? Is there a big ball of rock and metal or something down there around which, all this hydrogen and helium sits? Or is it just basically hydrogen and helium the whole way down? Do things just get more dense, hotter, more high pressure the deeper you go, but there's no actual nub of a planet at the bottom, and we just don't know the answer to that. We think there's a core, but the measurements we've taken so far, they're compatible with either one, and one of the big hopes is Juno will be able to actually nail that down.
Okay, and how exactly then does Juno figure this out?
Yes, obviously you can't just look. The atmosphere of Jupiter is incredibly thick. The planet's about 11 times the diameter of Earth. It's absolutely enormous. So what it's got on board is a very sensitive gravity detector, essentially. And as it orbits the planet, there'll be subtle variations in its orbit. And if you can get really good readings of how the planet's gravitational field looks, you can make some fairly strong inferences about what it probably looks like inside. And that's what they're hoping will definitively nail down whether this thing has a core or not, and if so, how big it is. And one of the things that, in turn, will tell you is it might help us answer this question, which is also a bit mysterious, of how exactly the planet formed.
And so why is that in doubt? Are there competing theories on that?
Everyone agrees that Jupiter, it formed from the same sort of primordial cloud of hydrogen, helium, and a few other bits and bobs that the whole solar system, including the sun, condensed from. But the question is, how did that happen? So one theory is that the dust grains sort of assembled into pebbles, the pebbles assembled into boulders, the boulders assembled into bigger boulders, and eventually you got something that looks a bit like a rocky planet like Earth. But in Jupiter's case, the rocky planet got big enough that it started grabbing all the hydrogen and all the helium from its neighborhood, and that's how it formed. And if that's what happened, you would expect that rocky core to still be there at the bottom. The problem with that is people think there probably wasn't time for that to happen. By the time you'd built a rocky core, the sun, which is ignited by this point, the pressure from its radiation would have driven all the hydrogen and helium away, so there's nothing for Jupiter to grab onto. So the second possibility is that it condensed from the hydrogen and the helium itself. There was some knot in the gas cloud that was just there, by chance, and the gravity and the physics was such that more hydrogen and more helium was pulled in, and the whole thing just ran away with itself. And if that's the case, you might expect to find either no core at all, or only a very, very small one, which is made up of elements that have been brought by comets, asteroids, and whatever else has been swallowed up by Jupiter since then. So one of the big hopes is that by finding out about the core, you can learn about how the planet formed.
Well, I mean, Jupiter's kind of like a mini solar system in its own right. It's got its dozens of moons and its magnetic fields and everything. I mean, I kind of wonder how learning about this tells you more broadly about how solar systems form in general. Where does this get us in terms of the really big question about the solar system as a whole?
Well, so there are two ways it does that. So one is it tells us about our solar system, and you can't really understand our solar system if you don't understand Jupiter, because the sun accounts for almost all the mass in the solar system, well over 99%, but Jupiter accounts for almost all of the rest. It's enormous. It's more than twice as massive as all the other planets put together, and its gravity does all kinds of things. It affects the orbits of the other 7 planets. It determines, the structure of, and the fact that we have an asteroid belt is probably down to Jupiter. A lot of the comets that come in from elsewhere in the solar system, their orbits are determined pretty much by Jupiter. So if you want to understand why the solar system looks like it does, you need first to understand why Jupiter looks like it does. And then there's a question of other solar systems as well. As Juno has been cruising to Jupiter, this question's become more and more pressing, because in the past, decade and a bit, we've discovered a whole slew of planets around other stars. These are these exoplanets. And one of the most common kinds of planets we found are things called hot Jupiters, which are big gas giants like Jupiter that orbit really, really close to their parent stars, like way closer than Mercury does in our solar system. The problem with that is, as far as we can tell, there's absolutely no way those things could have formed there, because that close to a star, there's so much radiation, the environment is just so fierce that these things would have been disassembled as quickly as they formed. So one of the assumptions, therefore, is that if they can't have formed there, then they probably didn't form there. They probably formed further out and then migrated in, which is also one of the theories about the early history of our solar system. So if you can get a really good handle on Jupiter's history and where exactly it formed, you'll have an idea of how it is these giant planets might be able to move around, and that might in turn tell you how to think about all these other solar systems that we're just in the process of discovering.
So Juno's going to tell us not only about how Jupiter formed, but possibly where Jupiter's going to end up, and also a whole bunch about what's going on with other solar systems out there in the universe. This is just kind of the latest in a long string of exciting missions, right? So last year we had a probe landing on a comet. We went past Pluto at great speed. It's all been great for at least interplanetary travel. What happens next?
Yeah, we've had a bit of a golden age. You mentioned New Horizons, you mentioned Philae on the comet. We've had rovers on Mars. We've had missions to Saturn and Titan. And for a long time, these kind of robot probes have been really hitting the headlines. And there's more stuff after Juno, but there's not as much as there was. And there's a sense that maybe this golden age is sort of coming to a bit of an end. So I think that's a shame in a way. I mean, people say robot exploration doesn't have the romance of sort of manned space travel. And I sort of get what they're saying. But you look at the reactions to things like New Horizons with all those pictures. A lot of people got kind of worried about Philae when it tried to land on the comet and it sort of didn't work and it ended up a long way from where it should have been. And
I was terrified for days.
Yeah, and because we can put these really high quality cameras on these things now, because we've got the internet to sort of disseminate disseminated, or if you want a front row seat to other planets in the solar system, you now kind of have one. So I think it's kind of a bit of a shame that we're not going to see anything quite this big, at least for a little while.
So I guess we sit back and enjoy what Juno has to offer.
Yeah, well, that's my plan anyway.
Tim Cross, thank you very much. And if you're following on the Juno mission out there, let us know on Twitter. We're at Economist Radio. Now, it may be very unscientific to gamble. After all, the numbers tell you that the house will always win. But in one recent study, the age-old desire to outwit an opponent at the blackjack table is helping us push the boundaries of what we know about the mind. Kevin Holmes is an assistant professor of psychology at Colorado College, and he designed a recent study using Blackjack, the game where players can choose to be dealt cards and the goal is to get as close to 21 without going over. He was intending to test, well, I'll let him explain.
Well, there's a lot of evidence that people think about numbers in a spatial way, that they tend to associate smaller numbers with the left side of space and larger numbers with the right side of space. And we were interested in whether this left-to-right oriented number line would manifest in an everyday game like Blackjack.
The team tracked the eye movements of blackjack players in the lab closely to see if those movements would vary depending on the hand they were dealt.
So participants, when playing Blackjack, looked more to the left when they had a hand with a smaller value, and then when it was a larger value hand, they tended to look toward the right of the screen.
The results seem to reveal a relationship between those eye movements and how we think about numbers.
One key result is that the eye movements were driven by the total value of the hand and not merely by the number of cards that were dealt. So if you're playing Blackjack and you're late in the hand, meaning you've been dealt 3 or 4 cards, you might expect that if you're moving your eyes, it's going to be in response to how many cards you have or perhaps the value of that last card. And although those do tend to be predictive of the eye movements, that's not the whole story. So when you control for those factors, the eye movements are still driven by the total value of the hand, which suggests it's really something about mental arithmetic.
Kevin says the experiment has meaningful implications for our understanding of how the brain approaches numeracy.
One of the bottom lines here is that space and number are very intertwined in the mind. These are very tightly connected. I think the implication is that whenever we're going about our everyday experiences, as we're thinking about numbers, we are relying on that spatial format. It's serving to ground what might otherwise be a kind of abstract concept.
To look further into this research into the gambler's gaze, I'm joined by science correspondent Matt Kaplan. First, Matt, what brought you to look into this research in the first place?
It's such a fascinating area because you have a lot of folks who justifiably want to know when they can look at another poker player and detect just how strong their hand is, because there is a science to that. But all of this stuff that comes out of card games is also really useful for understanding how the mind actually works. You've got this boundary between game and science, which ends up just being an awful lot of fun to explore.
Let's look at this particular experiment in a little further detail. How did it work?
The folks at Emory who are doing this research were looking at past research that said, well, when you ask folks to add stuff up and then you tell them to point on a number line at the value of whatever they've just added, they will tend to veer a little bit more to the right on the number line if they were conducting an addition than if they were conducting a subtraction. But what Kevin Holmes was asking was, well, wait a minute, does the value that you end up with have some sort of an effect on how far you lean? And that's exactly what they tested. They looked at the eyes of people as they were playing blackjack, and when they ended up with a large number towards the end, they found that their eyes tended to veer 0.4 degrees to the right if they had a 20 or a 21 in their hand. But when they had very low numbers in their hand, their eyes tended to veer 0.1 or even 0.2 degrees to the left. And there was a gradation, too, which was kind of cool. As their hands increased, they started to veer more and more towards the right.
So why left and right, though? I mean, I can see that there's a distinction between the two, sort of an opposite effect, but why one sum for left and one sum for right?
Well, one theory is that because we read left to right, we tend to associate left to right with left being the beginning and right being an end, and therefore as you add value to something with a sum, that you go further and further to the right. Something the researchers need to do is to replicate this experiment, but with folks from Israel who are fluent in Hebrew as their native language. Because Hebrew, as you know, you go from right to left. If your brain is focused on going right to left all the time, I wonder, and so does Dr. Holmes, whether or not all of these results would be reversed.
So, Matt, with this knowledge in mind, then, what's the next experiment? What kind of questions can we now start to answer?
The reality is that from a gambler perspective, this isn't particularly useful to folks playing blackjack, because knowing what's in someone else's hand in blackjack doesn't really help you. But what would be interesting is whether or not having a high-value hand that may not be numerical, something like a royal flush in poker, whether or not that leads people to veer towards the right. From a gambling perspective, that would be really useful, because if you could notice that people's faces are beginning to veer right when they get higher cards in their hands, man, that would be awesome for poker players to know, and probably be quite lucrative too.
So what you reckon is the next time I'm in a casino, I should keep an eye out for this effect?
I would certainly try it out and see if it works. And if you're right, boy, you're going to rake in the cash, Jason.
Thanks very much for that, Matt.
No problem, Jason.
So if you'd like to see some scientific gambling tips from Matt, or you'd just like to give us your 2 cents for free, don't forget there's email as well as Twitter. We're on radio@economist.com. Well, that's it from Babbage this week. I'm Jason Palmer from The Economist in London. Goodbye.